Okay, great. I'll start my sharing. Okay, so shall I start, Anna?
Yes, please.
Okay, great. So first of all, I want to thank everybody for joining in today for this talk, and thanks to Links for giving me the opportunity of presenting my work. Today, I'll be presenting before you a work on DNN based beam selection and millimeter wave heterogeneous network. Uh, I am Deepa Jagyasi and I'm working with Professor Maso. And this work has been performed at Links Laboratory. I'll begin. So, in general, millimeter wave communication, as we all know, is a very promising solution for handling the massive data traffic. Also, it has a huge unlicensed bandwidth, which can accommodate many users. So, it is a potential solution to solve the problem of data traffic. However, it is associated with some challenges which include the limited coverage, and it is significantly prone to the blockages such as the high density objects, walls, humans, also the raindrops, etc. However, on the other hand, if we see the sub 6 gigahertz macro base stations, that is the legacy base stations, they are they are good enough to provide the flexible coverage, and the coverage is good, and they're also densely deployed, which reduces the overall infrastructural implementation cost. But the sub-6 gigahertz base stations have limited bandwidth. So it is a good solution if we combine both these technologies to work hand in hand and provide a multi-tier heterogeneous network. Only for these reasons, the multi-tier heterogeneous networks are expected to be deployed in near future, which can uh, which can exploit the benefits of both the millimeter wave communication as well as the sub 6 gigahertz macro base stations. I would like to say, if you have any doubts or any questions, please feel free to ask in between. Okay, so moving on. However, so this is a basic heterogeneous network where the sub-6 gigahertz macro base stations will be accompanied by the small cells, and the small cells can utilize or benefit the high data rates, and the millimeter wave and the macro base stations will have the better coverage, hence providing the flexibility of movement. Further, in order for the millimeter wave base stations to be deployed correctly, uh, beam forming is a very important task which can overcome the path loss, and the multiple number of beams, multiple number of antennas which can be associated with a millimeter wave base station. There will be the possibility of multiple directional beams which can be chosen. However, selecting the best beam is a crucial task again, and the best beam which can provide the good communication link between the user equipment and the millimeter wave base station. This beam selection is an important challenge which needs to be tackled when we consider millimeter wave communication. So, beam selection in general was conventionally addressed in literature using the exhaustive search based techniques or the multi level selection approaches. The exhaustive search In exhaustive search, all the beams are scanned one by one, and the best beam, sorry, and the best beam which provides the maximum sum rate can be selected. Whereas we can think of a multi-level selection approach as scanning from coarse scanning to the fine tuning. That is, first the sector of the beam sector can be scanned and selected, which provides the optimal sum rate, and then out of them, individually, each beam can be selected, can be scanned to observe the best sum rate, and the best one can be selected. Okay, but both of these techniques are associated with a huge beam training overhead, which inherently introduces the latency, which is unacceptable for the scanning purpose. So, motivated by this, the deep learning and machine learning tools have come up which can overcome the latency. And this motivates us, in fact, to design a deep neural network based millimeter wave base station and beam selection method for a heterogeneous architecture to benefit from both the legacy sub 6 gigahertz base station and millimeter wave base station. And for this task, we utilize only the channel information which is available at sub 6 gigahertz base station. So using the legacy network CSI, we learn to obtain the best millimeter wave base station which can serve and the best beam which can be selected for performing the good communication, forming the good communication link. So um, this is the motivation for this work. Further, with respect to the related work, deep learning and machine learning based techniques have been largely studied for various communication applications, which include the channel estimation. It also includes the precoder designs. However, with respect to the, here I will discuss only the beam selection based communication application. So many of the works assume millimeter wave base station and ignore the sub 6 gigahertz base stations. However, so this was done by the beam selection task was performed while selecting only the millimeter base stations by these papers, wherein in this the learning based classification technique was adapted, and it was done by using the situational knowledge of the environment and also the location information of the user equipment, and the deep neural network was developed to perform the task. Further, different techniques were utilized by this by the authors in this, wherein the KNN, that is the K nearest neighbor support vector machines, and the multi-level perceptron were analyzed and compared to perform the task of beam selection while utilizing only the angle of arrival information. However, these work, as I said, were done only for while considering the millimeter wave communication and did not include the sub 6 gigahertz. So in respect of the heterogeneous network, the beam selection task was done by these two authors in these two papers, wherein the kernel-based learning was adapted, and it was done for a target discovery problem and handovers, wherein the location information along with the sub 6 gigahertz channel was utilized to perform the beam selection and blockage prediction for the single base station, single user equipment scenario. Again, these works consider the single millimeter wave base station, single user equipment in the vicinity of a single sub 6 gigahertz base station. But in this work, we extend to a coordinated multi sub 6 gigahertz base station and the coordinated multiple millimeter wave base stations serving a user. Finally, location is important parameter which can be utilized independently and can be used to do this task. And most of the works utilize the location information, for example, also including this. But it is known that the location information may not be readily available by many user equipments, and the location sensors, for example, the GPS, may have low accuracy. So in because of that, we intentionally eliminate the availability of location information in this proposed work and design the network which considers only the basic channel components from sub 6 gigahertz macro base stations. So finally, hence the contribution of this work can be summarized as we design a deep neural network based beam selection and base station predictor network for a heterogeneous architecture, while using the inputs only from the sub-6 gigahertz. Further, the coordinated sub-6 gigahertz base stations are considered. Then the problem is solved by designing the branch neural network structure, which formulates the overall problem into two subproblems and jointly devises the solution towards it. That is, two problems considered are the base station selection problem and the beam selection problem. Finally, we intentionally eliminate the location information from the set of the features for doing this task, and the feature vectors which are considered as the input include only the azimuthal and elevation angle of arrival at the base station, macro base station, the received signal power from the user equipment, and the signal phase and propagation delay. So based on these five components, we learn and obtain, we further do the task of the best millimeter wave base station and beam selection. So the considered system heterogeneous model is as here. So we assume that there are multiple macro base stations, that is sub-6 gigahertz base stations. So let there be bmu base stations. Each of the base station is accompanied with mu number of antennas. Also, there are bm number of millimeter wave base stations in the network, each associated with nm number of antennas. So it is assumed that the sub-6 gigahertz base stations are coordinated, and the overall processing of sub-6 gigahertz base station, which include the precoder designing, channel estimation, and also the deep neural network computations. All these processing is happening in the central cloud processor, whereas the millimeter wave base stations work in coordination with sub-6 gigahertz base stations and can serve the user with the higher data rates. So the scenario can be considered as the user equipment is always accompanied with the always associated with the macro base stations for better connectivity, and whenever the user is in vicinity of any millimeter wave base station, the macro base station will command the best millimeter wave base station and the best beam to the user for enhancing the sum rate or the capacity. So this is a scenario which we overall consider.
Excuse me, Deepa.
Yes, sure.
I just had a small question. So, is the user equipment considered here mobile? I mean, does it move a lot or is it relatively stationary?
No, for this work, we are considering only the static user, but our next work is on the mobility. That's a future work which we are
So,
studying.
once association is formed with the millimeter wave base station, it won't change throughout the service period, is it?
Yes, for the coherence channel time, it doesn't change. It is static
Uh,
for that time.
okay, all right. So, I mean, do you then actually gain any benefit from the millimeter wave stations being coordinated? I mean,
So
yeah.
we do not expect the millimeter wave base stations to be coordinated. In
Mhm.
fact, we assume that those macro base stations are coordinated amongst themselves to obtain the best beam which base station which can be serving the user at that time.
Okay, all right. Thank you.
Okay, so this is the environment in general which we consider, and um, so overall, our problem formulation can be defined as the aim is to obtain the best base station, millimeter wave base station, and also the best beam, which can maximize the overall achievable sum rate for a given user. And this is done by utilizing only the sub-6 gigahertz channel information. So hence, the optimal beamforming vector, which can be devised as the argument that maximizes and obtains a beam, the vector Vm, which is chosen from all possible vectors dictionary V, and that maximizes the overall sum rate. Finally, to solve this again, we formulate two subproblems. One is the base station selection problem and the beam selection problem. So base station selection problem is solved by using a classification approach, whereas the regression based mapping or the regression based problem is formulated for the beam selection. Why was that done? I'll explain in later slides. So in general, we can say that the feature vectors, that is F mu, these are from the macro base stations, are mapped to the probability mass function of the millimeter wave base stations, and the base station which provides the best probability would be selected in general as the output of the learned network. Further, the F mu, that is again the features from some macro base stations, are mapped as a regression based problem, whereas RB are the achievable rates from equation 1, achievable rate from each particular beam, and the beam with the maximum achievable rate would be selected as the output of the beam selection problem. So these are the mappings which were formulated, and these are a nonlinear mapping which can be learned in a better way by a neural network. So to learn from the features, the deep neural network architecture was developed as this, which has three important parts to be done. That is, number one is the base network, and the output of the base network is given to two separate networks. One is the millimeter wave base station selection network and the beam selection network. So this output is a learned output from the base network, and further these learnings are provided to separately to both the networks. As these two problems are not mutually exclusive, we have also a mapping between the base station selection and the beam selection. So in detail, I will explain each of the network as so the base network was basically designed to understand or learn the importance of the features and the mapping between each feature. So the input towards this network is concatenated features from each base station, that is each sub 6 gigahertz base station. And the first convolution layer was added to learn the correlation between feature vector of each base station. So that's why it is 1 cross NF. So each base station, within each base station, what were the weights or what was the correlation among the features was learned in a successful way by the first convolution layer. Further, the second convolution layer was added to learn the features correlation among multiple base stations. So this will help learning in a better way. And then it was passed to a dense network to for providing better learning, which output of which is given to the base station selection network and also the beam selection network. So this is after learning the importance and the correlation among the features and among the base stations which are serving the user. So once we have these learned features, dense learned features, which is given to the millimeter wave base station network. So the input to this base station network is the learned features from the base network again, and by using the dense layers, it ultimately understands the probability of the base station which will be utilized to serve the user. So hence the output of this is finally projected to BM feature space, wherein the BM is a number of millimeter wave base stations, and the final activation is softmax to understand the probability mass function for each of them. Just before that, the learned output of this network is also given to the millimeter wave beam selection network, because once the base station is selected, after that which beam would be selected is important, and these two problems are not exclusive. So for that, the input to this network is again from the base network learned features, and also the concatenated, and it is concatenated with the learn features from the base station selection network. So the inputs are then also passed to the fully connected dense layers, and finally they are mapped to m dimensional space where m is the number of beams which were possible. So here we consider a regression based output, that is the each output, each node at output results in the achievable sum rate, and the beam with the best sum rate will be selected. So here the concatenation was done only because to understand the better, to make the learning better, which was from also from the base station selection network.
Deepa, can I
Yes,
ask one question?
sure, sure.
Yeah, so I understand here the best beam is the one that maximizes the subrate value, right? But
Yes.
is it always the case for 3GPP or the 5GNR where, so to my understanding, that the best beam is something that you have the CSI characteristics and then you choose the best beam based on the what is the received maximum received value signal power
Yes.
at the user or at the base station, where depending on whether you're transmitting downlink or uplink.
Mm-hmm.
But is there any, is it always like, is there any standard or something like that where the best beam is chosen such that it maximizes the sum rate rather than not just the signal received power or something?
Sanket,
I'm
so
not sure about that.
I am frankly also not sure about the standard of which is to be used, but here the understanding was to establish the best communication link between the beams, right, between the millimeter base station and the user. So aim is to maximize the sum rate at the user end, that the data rate achieved by the user is always good. So, but frankly, I am not aware about the standard, but I believe the sum rate is a good evaluation parameter that can be utilized.
Okay, thank you.
Yeah, but I would like to hear from if anyone knows about the standard with this regard, and
Yeah,
maybe.
because this is what I remember from one of the our Nokia Bell Labs colleagues, Fuad. He gave talk last year on this
Okay.
beam selection and reselection policies. And
Mm-hmm.
from what I understood from his talk, is it was like basically it depends on the received signal power. So you have the CSI, you estimate the CSI, and then
Mm-hmm.
you check the CSI, you select the beam, for example, round robin or multi-level things that you mentioned,
Yes.
and the beam that gives you the maximum received power at the user is usually selected for the transmission. And
Mm-hmm.
means I did not remember that whether he said anything about maximum separate there.
But sum rate is indirectly connected to also the received power
Right, right.
in
Yes.
general. So yes, but I will definitely take a look. Thanks.
Thank you.
Yeah, so that was the idea behind selecting this optimization problem, that we want to maximize the overall sum rate and obtain the best communication link. And the by learning this way, it was the job was done, frankly. So, but in order to have achieved this architecture, neural network architectures, it was selected only after many experiments which were done before. So here I will try to discuss two of the most prominent experiments which were done, and the reasons why we did not pick them. So the experiment one included a multi-layer sequential DNN network. So it was very simple at first to assume that all the base station network, all the macro base station features can be concatenated. So input of that network was concatenated base station's features, and the output would be also the concatenated beams and the indexes, which will demonstrate all the millimeter wave base stations and all the possible beams. So, and the learning will happen using the dense layers. So this network was very simple, and it also does the task, but the problem associated with it was once we increased the number of base stations, millimeter wave base station, the output dramatically increases. So for every single base station, there were 64 nodes which has to be concatenated as the output. So if any changes appear in such a network, it requires extensive retraining, and it wasn't flexible enough for small variations. So we did not move forward with that network and instead developed a branch network which separately does the base station selection task and the beam selection task, like the one we have developed now. But initially, we considered both the problems as the classification problem. So by adapting the branching, it improved the learning. It was a good solution. And now the network was more flexible as compared to the previous one and was able to adapt small changes. That is, we didn't have to change the output nodes dramatically and drastically. So, but the base station selection problem as a classification problem was also performing well. However, when we talk about the beam selection problem, in millimeter wave, it wasn't performing well. The classification was not probably the best choice because with millimeter wave beams, millimeter wave communication, there are many large directional beams, and the angular difference between any two adjacent beam is very tiny, is very small, which causes the overlapping, and it is possible to have multiple best beams which can communicate and provide equivalent performance. So classification based technique was not a very good solution, and finally we selected the regression based solution for that problem, wherein we have the exact values for all the beams performance, and the best beam performance can be selected. In fact, if we wanted to select the top K beams or top P beams, we could have selected using this regression based solution. So hence, by these experiments, we evolved towards network architecture, which is currently proposed, and it performed well. So here are the results, which first I will explain the simulation environment. So the data set which we utilized for this work is open data set available by the authors in this, and it is a outdoor scenario. This data set is considering multiple obstacles or multiple buildings, each with different height and have different materials. Hence, the reflection and the blockages are considered are inherently included in the data set. So based on that, we selected the two sub 6 gigahertz base stations uh, uh, operating in a coordinated manner, and 8 millimeter wave base stations, whereas the users are associated on the block, on the blue blocks. So the red ones are the millimeter wave base stations, and the green are the sub 6 gigahertz base station, and the users are densely located on this grid. So hence, by using the channel information at these base stations from the users, we learn and then command the best millimeter wave base station and the beam which could serve the user at any time. So these are more detailed parameters, hyperparameters for this scenario. That is, so we consider number of base station, active base stations were 8 and 2 3.5 gigahertz base stations, and these are the users grid. So finally, these are the results which we achieved. So here this plot demonstrates the total accuracy versus the ratio of the training data. Here by total accuracy I mean that is the accuracy of successfully selecting the best beam and the best base station and the best beam. So both the selection were done correctly. That is a total accuracy. Further, the training data set is varying on this axis, wherein the training was done. The overall data set was divided into 80 and 20% ratio. That is, the 80% data set was utilized for training and 20% was utilized for testing or validation. And out of the total 80% data set, these are the ratios or the percentage where one was the overall 80% data set. So when we plot the accuracy versus the data set or training data ratio, we observed the achievable base station accuracy was 97%. So the red one is the base station accuracy, whereas the beam prediction was 88%, and the total accuracy when both were correct was 86% with the total data here. Also, the comparable performance, the plot has become almost converged, and the comparable performance was done using the 50% training data set as well. Hence, the network is able to learn even with a small subset of the overall data set. So it implies that from this figure. Further, we experimented while observing the accuracy with the number of epochs. That is, we varied the epochs, and now we intentionally included a location to compare the performance with and without the location. So the blue curve is the accuracy for with location, and the others are without location, wherein the difference is while selecting the best one beam and the best three beams. So obviously, as expected, the location aided information performs better, as that is more number of features and strong information is available. So it performs better, but the gap between the performance can be reduced by selecting the top B beams instead of only one optimal beam. So if we have options and we select top B beams, we can reduce the gap between this, and the network can utilize also without the location. Finally, the accuracy with respect to the number of beams predicted, that is here only one beam was selected, and here number of beams selected were increased. So that is the performance with top 5 beams, for example. So, and this is demonstrated, or this is plotted against a varying training data set, that is with 5%, 30%, 50 and 100%. So 100%, I again mean that it is overall the 80% of the complete data which was utilized for training. So as expected, the accuracy increases with increasing training data. With also the accuracy increases with selecting more number of beams. But also with this plot, we can understand we can get some insight about the latency. That is, if it was an exhaustive search, it would have performed the scanning through M received power measurements. That is 64 for a case, that is total number of beams. However, with learning-based approach, the 85% accuracy can be achieved with best three beams, and hence the overall latency of the network can be reduced. So learning-based approach can have the good solution, can provide a good solution when the latency is important, and it is not exhaustive, it is not intense like the exhaustive search. Okay, finally, I would like to conclude by presenting some conclusions and the future work. So in this work, we presented a proposed branch deep neural network model that jointly performs the task of millimeter wave base station prediction and a beam selection for a heterogeneous environment, wherein the sub-6 gigahertz are co-located with the millimeter wave base stations and benefit from both the technologies. The base station prediction task was formulated as a classification problem, whereas the beam selection is formulated as a regression problem. And we utilize the features available only at the sub-6 gigahertz base station and learn the bijective mapping for analyzing for obtaining the best millimeter wave base station and the best millimeter wave beam. Intentionally, the location information is excluded as the location information may not always be readily available. Finally, on comparison with the exhaustive search, we obtain the success probability of roughly the total accuracy of 86%. And in future, we are motivated, or we are extending this work for more complex scenarios while considering dense environments and blockages, and also while considering the mobility profiles of the users. So the related publication is there here, and you can read more about this paper on this link. And, thank you.
Okay, so do you have some question in your hands?
Hello.
Yeah, so I have one question regarding the latency. So I
Mhm.
understand the motivation behind using this machine learning technique is to reduce the latency with respect to exhaustive search. Right? So what happens means sorry, I can hear echo
Yes, there's a
echo.
lot of echo.
So, hello.
Yes, yes,
Yeah,
Sanket.
sorry. Yeah, and so Deepa, I understand that if you the same 80% accuracy can be obtained using three beams compared to the exhaustive search where one has to search for the M beam through M beams, right?
Yes.
So, but does it consider this training overhead? So, for example, there is a coordination, as you said. For example, these inputs are from the channel states that are seen by the sub 6 gigahertz base station. So you have to get the input, and then there is a coordination, and then there is a training overhead. So, does this
Yes.
latency means when you compare this over training latency? So, when you train the network plus this beam selection latency, how does it compare with the exhaustive search latency?
So, Sanket, we've not done that analysis for this work, but I am currently doing it for my next work, and we in general observe how much time our algorithm is taking per epoch to train and learn, as compared to how much time is the overall coherence time for selecting the base station. So we selected average time, coherence time, and we are observing the algorithm, how fast or computationally quickly it is running. So we are having a lot of buffer at least uh, each beam selection, the time which is dedicated in general by the standard, we are at least 1/10 time. We are taking 1/10 time, which is having a lot of buffer, and hence we can demonstrate that in our next work definitely that the latency is in good hands. Yeah,
Okay, well, probably
it is
one
very
suggestion. Yeah, sorry. Yeah,
sorry.
yeah, please.
Yeah, so with that, we are proving, in fact, that the latency in general uh, it is okay to consider it, and it is not overriding the standard time.
Okay, but I think there are some intelligent way itself rather than exhaustive search. For example, there is a, if I recall correctly, there is a two-level search. Like for example, you rather than going for beam by beam, you
Yes.
create some kind of a big sectors, and then you see which sector is giving the maximum or the best beam among that sector, and then you just focus on that particular sector rather than going for all 360 search for the beams. You focus now only on that sector, and you just do kind of an exhaustive search within that sector. I think
Yes.
that gives us a lot of latency compared to the
Yes.
exhaustive search.
Yes, yes, yes. I was mentioning, that is a multi-level, multi-level selection process, wherein there are multiple levels. That is the sectors, like you said, and in each sector, the number of beams will be scanned one by one. Yeah, that reduces the latency. But again, it is proved, and it has been said that it will not. It still is computationally expensive to scan. Hence, only for that reason, the machine learning, as it gives the one-shot solution, is considered to overcome those challenges.
Okay. One last question is, I see that you use this sub-6 gigahertz channel information to predict the best beam, right?
Yes.
Yeah, so it's unclear to me that I see that, for example, if sub-6 gigahertz, the channels are different when you go for the mmWave because probably you have the line of sight communication or no line of sight communication.
Yes.
And basically, when you have line of sight communication, probably it is better to model those channels using Gaussian fading or Nakagami fading, right?
Yes.
But
Yes.
rather when you have the sub-6 gigahertz, you have a lot of reflections, and then it is usually the trend that people model it using Rayleigh fading. Then how does
Uh,
it accurately
yes. In
map
fact,
the mmWave
I,
channel?
yes, in fact, I was also myself curious about utilizing it, but sub-6 gigahertz is well deployed, and it is proved mathematically that if there is a learning on the base station, there is a bijective mapping which can be created between the sub-6 gigahertz base stations and also the millimeter wave beams or the millimeter wave base station. So in one of the paper, authors have proved that the bijective mapping can be created, and the sub-6 gigahertz channels are not in fact totally different. So definitely millimeter wave has some extra components, but it the overall network can learn, and the bijective mapping can be created. Only while referring that, I can in fact share that mathematical proof with you.
Yeah, sure, thank you.
After that, it is a very interesting work, and it clearly proves that it is possible to understand about other type of networks, even millimeter wave or even terahertz networks, if there is availability of a bigger area like sub 6 gigahertz. So they have created a bijective mapping, proved it in fact. So
Okay.
I'll
Yes,
share
okay.
with you in fact.
Yeah, thank you, Deepa.
Okay, so do we have other questions in the audience?
I have one, if I may.
Yes, please.
I've followed your talk with attention, and it was quite striking to me that you insisted that you are not using localization. I was wondering, have you ever thought about using your method for localization, or tried whether your neural network has actually any sort of interesting property? Because I believe that the beam selection problem has a lot to do with the kind of localizing a point in a space. So I was wondering whether you have some sort of evaluation of the accuracy of your method for this other related problem.
We have included the localization in the network to only understand the comparative performance for our method, but we were focused to avoid the location or any available data through sensors or LiDAR or camera input, only for the fact that they may not be available for low power devices, and for example in IoT they cannot share the information, and it is difficult to obtain the location information all the time, whereas by using the standard channel information, it was possible to achieve little comparable performance. It is not optimal like the location based ones, but it can still perform comparable. That was the aim. And yeah, so for now we are not using even the localization for extension of this work, which is mobility and
Sure.
complex scenarios.
My question was slightly different. It was about the problem of localization solved through your method instead of using localization information as input to your method. So it seems to me that in your representation from the sub-6 gigahertz information, there is a localization component embedded.
Yes, yes.
I was wondering whether you could extract localization information from the running of your neural network instead of
Yes,
using it for beam selection. So that was the question.
yes, yes. Sorry, I understood your question. I'm sorry, but for the prediction based for the mobility, we think that the localization information can be extracted, but we have not considered it now. But I will definitely try to incorporate or try to see if that can be done. Thank you for the input.
Okay, thanks. Interesting work.
Hello, can you hear me?
Yes, yes.
Okay, thank you. So thank you for the interesting talk and work. I have a question about the real applicability of your approach. So if I understood correctly, you try to use classification and regression in order to avoid an exhaustive search among all the base stations and all the beams. But
Yes.
in order to train your neural network, you need to do an extensive search, etc. So it's like you move the problem somewhere, and so I wonder how many, if you calculated a bit, how many years of data you need to collect with traditional methods like exhaustive search before your network starts to be effective. And also, have you tried to train your network on a certain scenario and then test it on another scenario? Because so far your results are with training and test set on the same scenario, which is too optimistic. Yes, so these are my two questions.
Yes, for the first question, I think that the exhaustive search, how much exhaustive search data is required is it is basically trained on the open search data, which has 10 million users data, and the ground truth is generated based on the ray tracing based approach. However, I am not sure about the number of years of the ray tracing data which can be required for training it, but with the fast moving user density, I believe it would not take too long, in fact. Whereas for the second question, the training and testing data was totally isolated. We did not test on the same data. In fact, that is the reason we isolated part of the data for testing, and training was done on different percentages. So if that answers.
Yeah, thank you.
Question.
Thank you for the first answer. For the second answer, maybe I will clarify the question. So in my understanding, the scenario is the same. I mean, the obstacles, the physical space. So I wonder if you tried and if you think it's interesting to try to train your network on a certain scenario with certain obstacles, etc., and then
Okay.
or a different scenarios, and then
Yes.
see how it behaves in a new scenario that your network hasn't yet seen.
Yes, I will try to also isolate the environment for that fact now.
Okay, thank you.
Thank
Thank you.
Is there any other question? Well, if not, I'd say that we can thank very much Deepa for her presentation, and we'll meet next week for our seminar series. Thank you very much to you all.
Thank you,
Yes.
Deepa.
Thank you all for amazing questions. It will definitely help me improve my future coming work.
Thank you for
so
a nice
much.
lecture. Thank you.
Thank you.
Thank you very much.
Thank you.